All right, folks, we are on our final lesson of 2.8. Let's finish this off. We're going to factor some special polynomials, and one that is really common. You use it a lot in pre-cal 11 especially, is called a difference of squares. Now, I want to recall something really quick. We should know our perfect squares. They should stand out to you as special numbers, and they are, again, whenever you take our 3, 4, whenever you take, we're just going to focus on the first 10, okay? And if you square these first 10, okay, we will get our perfect squares. So this list of numbers is always handy to have memorized and have available because they need to stand out as special because you're going to use them a lot. So 1 squared's 1, 2 squared's 4, 3 squared's 9, 4 squared's 16, 5 squared's 25, 6 squared's 36, 7 squared's 49, 8 squared's 64, 9 squared's 81, 10 squared's 100. And hey, let's just throw 11 squared in there is 121, and 12 squared is 144. Okay, those should all stand out as very special perfect squares, or PS for short. All right, so what is a difference of squares? Well, remember difference, okay? Difference of squares is just that, a difference. Difference means subtraction, okay? Okay, of two square numbers. All right, so what could that look like? Well, I could take a variable and square it. That's easy. So we'll call that x squared. And the difference is going to be the subtraction. And then let's put another square, a perfect square of 36. Now let's label a few things. What's actually going on here? Well, of course, this is a square, or a perfect square technically, because it's x times x. This is a perfect square because it can be written as 6 times 6. And this here tells us that we have a difference. Okay, so now we can see it's a square and its difference. So this is a binomial. Okay, it only has two terms when we look at it, but we can transform it into a trinomial by adding what's called a zero term. Now, this is a bit of an advanced method you may have not seen before, but a zero term is basically adding or putting a zero into an expression so you can better understand what's going on. And we can do our usual method by that. So what does that mean? Let's take a little look. So let's start with that same example above. We're going to start with x squared minus 36. This is a difference of squares. And we're going to add the zero term. So that looks like x squared plus 0x, because we could add, because you're wondering, well, where is the middle term? It's not there. Well, we can write it as a zero term because we always have the form ax squared plus bx plus c. So this is the case where b equals 0. Okay, now what do? Well, we can factor this. We know right away that we can find our magic numbers. We have a leading coefficient of 1, so we can use the shortcut. So what two numbers multiply to give me negative 36? So what two numbers give me negative 36? Well, also, now this is where the zero term comes in, sum to give me 0. Okay, well, we know what those are. It's 6 and negative 6. Okay, that's the only way we're going to get that to work out. We need 6 and negative 6. And so we can go right to our answer. We can write our two binomials in brackets being multiplied. I'm going to write my x's, and then my magic numbers are negative 6 and plus 6. Okay. And so this is a special case called a difference of squares. And if you recognize it, again, there's a better shortcut. You don't have to add the zero term. You can skip right to your answer quite quickly if you know your perfect squares. So what I'm saying here is adding this zero term can get a little bit tricky. Okay, especially if the binomial is a little bit more complex. This was an easy example. So instead, we can just notice a basic pattern. So what is our pattern? Well, we can write it as, again, x squared minus 36. Let's use the same example. But I could rewrite it slightly as saying x squared minus 6 squared. Okay? Now I can see, oh, that's a square, that's a square. And my answer is always going to look like the following. Whatever is being squared first is going to be the square root of it, or what is being squared, which is x. And whatever's being squared here is going to be, one's going to be subtraction, one's going to be addition. Again, doesn't matter what the order is. So one's always plus, one's always subtraction, okay? Now, how could I write this in a general way? Really easy. If I have something squared, let's call it a, and a difference of another thing being squared, that's very easy to go straight to factoring it by saying, well, the thing that's being squared, let's subtract it with the other and then add. This pattern will work every time with difference of squares. So if you recognize that you have a square and you have two perfect squares, essentially, you can go right to its factored form using this trick. So let's factor these completely. So first one here, I have x squared minus 16. Well, x squared, of course, is a perfect square. 16 is one of our perfect squares. That is the same as 4 times 4. So I'm just going to show that I have x squared minus 4 squared. And so I can go right to my solution of x minus 4 times x plus 4. And you're done. That's what's so nice about this shortcut. Moving on here. Now, I know this looks a little different because the negative is out in front, but of course, we need to check. I didn't do it in the last one because I had a leading coefficient of 1, but we need to check for a GCF first. This is what we learned last lesson. Okay, and we do have a GCF here. I can divide out a 4. So 36 and 4x squared, I can divide out the 4. So we're going to do that first. That's going to leave me with 9 minus x squared. And then I look at these two terms. Are they perfect squares? They are. I could rewrite it as 4 times 3 squared, and x squared is already a squared term. And now we can go right to our solution. Let's write our pair of binomials, and I take the 3, subtract the x, and I take the 3 and I add the x. Now I know it looks a little different with the x being second, but there's nothing wrong with that. We can leave it as is. Next one here, we got a couple perfect squares. We have an x squared, we have a 36, but this plus is a problem. This is a sum of squares, not a difference. This is a sum of squares, which actually you cannot factor. Let me show you. We cannot use our trick, so don't let this slip you up and think you can go right to the answer. Okay, what we're actually going to do is I'll show you that if I put in the 0 term like before, x squared plus 0x plus 36, I need now two numbers that multiply, okay, to 36 while also adding to 0. Well, if you think about that, the only way I can have two numbers multiply to 36, they either both are positive or both are negative. So they're both positive or they're both negative, okay, to get 36. Well, if I'm adding two positives or adding two negatives, it's impossible to get 0, okay? It is absolutely impossible. The only way that could work is if they were both 0, but of course 0 times 0 doesn't equal 36. So this results in a situation of non-factorable. All right. Again, check for GCF first. Again, I had a leading one here. I should have mentioned that there is no GCF. Here, no GCF again. And you might say, is this a difference of squares? This is a bit of a tricky one. When you see a 4, okay, that's a bit of a hint that maybe there is a way to write that as a square. And there is. We could rewrite this as x to the 2 to the 2. Okay, we can take x to the 4 and turn it into a square of x squared. And of course, 1 is the same as 1 squared. So now I have a difference of squares, and I can go right to my solution. So I'm going to write x squared minus 1 and x squared plus 1. And a lot of students stop here and say they're done. There's a problem though, is always check, am I done factoring? And this again, right here, we have another difference of squares. So these difference of squares, very often when you have this 4, they tend to pop up again. So don't let that trip you up. This is a difference of squares. So D of S for short. So we're going to do our same method. Okay, this can be written as 1 squared, and we're going to write 2 new pairs of brackets for that one, and I'm going to copy down, let's color code this. I'm going to keep the blue one, the x squared plus 1, because that's a sum of squares, which we know we can't factor that. Okay, so again, using our method, this now is going to be just x minus 1 and just x plus 1, because that was our difference of squares coming from here. Okay, let's flip the page and move on. Enough of difference of squares. We'll still see them and you got to be prepared to deal with them, but we are going to do polynomials with more than one variable. We're going to use everything we've learned in these next few questions. Okay, so first thing first, is there a GCF? Okay, that's what we always want to check. And right away, I know there is the GCF of the coefficients is 1 because there's a 1 here. And there is no common. I have an x in the first two, but not in the third. And I have a y in the second two, but not in the first. So I don't have a GCF. Okay, so I'm checking that first. There is no GCF. Okay, but I have a trinomial. So I'm going to go right to my magic numbers. Okay, so how are we going to work through this is I'm going to take this number times this number, as we know, 1 times the negative 21. And we can use our shortcut because I have a 1 there. Okay, but I'm not going to. You're going to see why in a second, because I want to emphasize, because we have two variables, I want to be careful and not just skip straight to the final answer. So that means I need to find two numbers that multiply to give me negative 21 and add to give me the middle coefficient, which is 4. Yes, I know there's x's and y's. We'll deal with that in a second. And those two numbers are going to be 7 and 3. 7 and negative 3, because 7 plus negative 3 will also give me 4. So let's do the decomp now. So keep my first term of x squared. Now remember, this one has an x and a y, so plus 7xy minus 3xy's. And I still have my last term of negative 21y squared. Okay, we're going to factor by grouping, and recall that that means take the first two and then the second two and factor them separately. So my first group here, I'm going to factor out, it looks like I can factor out only an x, leaving me with x plus 7y. And in my second group here, I can take out a negative 3 and a y. So I'm going to take out a negative 3 and a y. That's going to leave me with x plus 7y. And check it out, my brackets match, so I know I'm good to go. I can factor out the x plus 7y, and I'm left over, my leftovers is x minus 3y. Check, can I factor either of those? Nope, definitely not. No difference of squares. We are done. Okay, now you might say, well, maybe I could have used the shortcut. And yes, but you need to be aware that if there's an x and a y, okay, x squared and a y squared here, that you're going to need an x and a y in both of your binomials. Okay, but yes, my magic numbers of positive 7 and negative 3, we can see did occur here and here. So the trick does still work when you have a leading coefficient of 1. Just be careful keeping track of your variables. Okay, 2 left and we are done this unit. So the next one here is 9p squared minus 4q squared. You might look at that and say, well, there's two terms. Is this a difference of squares? Well, the 9's a perfect square, the 4's a perfect square, and the p squared and the q squares are, of course, by definition, perfect squares. So let's rewrite it like so. 3p squared, and then the square root of 4 is 2, which gives me 2q squared. And now I can go straight to my method here of factoring two binomials. I should have mentioned first, apologies, there was no GCF. Always check that first. Okay, and now left to that, I have my 3p and my 3p. I like to then write my other terms sometimes and go 2q, and then a difference of squares means one subtraction and one's addition. Check if I can do any more factoring. I cannot. We are done. Okay, let's do one last one. This will be the toughest one we handle here. Okay, there are more challenging ones, but this is as tough as we're going to get today. Let's see what we get. All right, GCF first. This time there is one. Okay, let's check all three terms. So 6, negative 26, and 20. My GCF there is a 2 for my coefficients. And it looks like from all three of those, I can take out 1x because there's an x to a 3, 2, and a 1. I can't take out y's because the first term doesn't have any, so I can take out 1x. Now let's rewrite. I'm left with 3x squared minus 13 xy plus 10y squared. So now we have a question, a trinomial that is really similar to this first one we did. However, I don't have a leading coefficient of 1. I'm still going to have to do decomposition using my magic numbers. So let's do that and we'll be done. Take my 3 and my positive 10. We're going to multiply those. So now we're going to find out two numbers that multiply to give me 30 while adding to give me the middle term, the middle coefficient of negative 13. And that's going to be, after a little bit of trial and error and searching through your factors, you're going to discover that that's going to be negative 3 and negative 10. So negative 3 times negative 10 equals positive 30. Negative 3 plus negative 10 gives me negative 13. Let's decompose our middle term. Please don't forget to write the 2x still hanging out in front. We have our first term we didn't touch. Let's decompose to negative 3. Don't forget both variables, x, y, minus 10 xy plus 10y squared. All right. Let's factor by grouping inside. Again, carry the 2x down. And this first pair, I'm going to factor out a 3 and an x, leaving me with x minus y. Yep, that's correct. And then in our next one, I can factor out a negative 10y. So factor out negative 10y, leaving me with x minus y again. Okay. And let's finish off one last step. We're going to finally factor out this binomial of x minus y. And I'm left with 3x minus 10y. Now, this is always a good one that is challenging to actually multiply this whole thing out if you have time during an assessment to make sure you did do it correctly. And we are done, folks. Now, you're going to notice in your notes, one thing to add is this super handy factoring flowchart, which will help you when do you use what method. And essentially, it comes down to this. Always check for a common factor first. Can you take out a GCF? Then based on how many terms do you have, if you have a trinomial, you're going to do decomp. If you have a binomial, you're going to do difference of squares, just because it's faster and easier. Okay, now factor and decomp, we realize that there is a pattern, so don't forget that we can take a shortcut. If a equals 1, if this term here is 1, we can take our shortcut and go right to our factored form. But that's it. That's all, folks. That is everything for Unit 2. Yes, there are 8 sections. A couple of them are very small, and we're going to move into review from here on out before we take the unit test. We'll see you in class.